If you've ever played a game with a moving enemy, it probably moved using pathfinding. Whether it moves in just a straight line towards the player like slender tubbies, or runs across an entire 3D terrain to get from A to B like in Skyrim, it would have used some form of pathfinding algorithm. But what uses does pathfinding have? Pathfinding has many uses. For example, Grand Theft Auto 5 uses it for the car's navigation system on the minimap, showing the player how to get from point A to B via roads using each junction on the road as a node. Most top-down tank games use pathfinding so that the enemies can get to the player. These usually use a square grid using each square as a node, which is what I'll be showing you today. Blinky, the red ghost in Pac-Man, also uses pathfinding, using the player as an ever-changing goal to chase him around the map. There are many different types of pathfinding algorithms, such as random backstepping, obstacle tracing, breadth first search, depth first search, best first search, vector field pathfinding, Dijkstra's method, A-star. Then, there are the different variations of A-star.
LPA star, HPA star, SMA star, beam search, deep dynamic weighting, whipside directional search, A-star, planning A-star.
But don't worry, you don't need to learn all of those. These are the three we will be comparing today. Dijkstra's algorithm works by checking each closest point that has not yet been visited in all directions, and it keeps expanding until it has found the goal. The algorithm is guaranteed to find the shortest path to the goal since it checks all of the nodes, but there is one big disadvantage. Since it checks all of the nodes, it will start to get a lot slower the longer it runs, since it's checking more and more nodes each time it expands, as you can see in the example on screen right now. Vector field pathfinding calculates the path to the goal from each individual node on the graph. It then gives each node a direction that points to the next closest node to the goal. This method is great if you have a lot of objects trying to find a path, since the algorithm only needs to be run once or every time the goal moves. However, this method can be very resource heavy on larger maps, since every single node needs to run the algorithm. A-star is a variation of Dijkstra's algorithm that is used when trying to find a single destination, and starts by expanding in the direction that seems to be closer to the goal. A-star uses both the distance from the start position and the distance to the goal when finding a path in order to find the shortest route. It will look at the nodes around it and comparing the f-costs of those nodes, and it will select the node with the lowest f-cost and then repeat until it has made its way to the goal. So what is a node? Each traversable point on the graph is called a node. In A-star, a node will hold three main values: the g-cost, the h-cost, and the f-cost. The g-cost is how far away that node is from the starting position. The h-cost is the distance from the end node using the Manhattan distance, which is the distance between 2 points in a grid-based graph on a strictly up, down, left, right path. It is called this because of Manhattan's building layout. And finally, the f-cost, which is the g-cost, and the h-cost just simply added together. So let's have a look at how the algorithm works. On screen you can see a square graph with a red square, which is the goal, a green square, which is the start. A-star will start by searching all the nodes around the start, and then calculating the g-cost, which is 1 because it has moved 1 square from the start node, the h-cost, which is 3 because it is 3 blocks away from the goal, and the f-cost of each node, which is just the h-cost and the g-cost added together. It will then select the node with the lowest f-cost and repeat the process from that node. This will continue until the algorithm finds the goal. Once the goal has been found, the program will trace back the path to find the shortest route. After all that, I bet the one question you've been wondering is, how do I represent my nodes? Well, let me show you some examples. The popular game Simpsons Hit and Run used a triangle or a polygon mesh for pathfinding and collisions. This is sometimes referred to as a navigation mesh, but we will not be covering this in the video. A link can be found in the description if you wish to learn more about it though. Counter-Strike uses a quad tree for the pathfinding for the game's bots, so they can navigate around the 3D terrain using ladders, jumping over obstacles and just not getting stuck. Quad trees are square grids that don't have to be the same size, so large empty spaces can be represented by one node instead of lots of separate nodes, as you can see in the image displayed on screen. But for simplicity's sake, the type of grid we're going to be using is a square grid. Alright, let's start making this in Unity. Here is the final project. As you can see, when I left click, the target moves to the mouse position and a red path is generated between the start position and the target. So here we are with an empty scene. First, we're going to want to create the 3D plane so that we have some idea of where the map is going to be. I'm also going to quickly add some cubes as obstacles so the path isn't just a straight line. I'll also give these obstacles a new layer called wall so that we can distinguish them from the floor plane in the code. And we'll apply this layer to each of the obstacles. I'm going to create 2 cubes, one to be the start position and another to be the end position. We want the end position block to move to the mouse position when we click, but this isn't part of Pathfinding and the program can be run without it. I'm going to quickly paste in the code and you can pause if you wish to include it. I'll also create a red material just to distinguish the 2 blocks from each other. So now on to the real stuff. To get the program to work, we're going to need 3 scripts. One called Pathfinding, which will contain the A* algorithm. One called Node, which will contain a class for nodes. And the last one will be Grid, and will draw and hold information about the square grid. The one we'll start with is the Node class. First, we'll remove the mono behavior since this script doesn't need it. We'll add 2 variables so we can check what position in the array, which we'll be creating later, the nodes are at. We'll call these grid X and grid Y. We'll add a boolean so we can tell whether or not the node is being obstructed or not. A vector 3 called position to track the node's real world position. A node called parent, this is for the A* algorithm so that it can trace back the path it has found to the beginning. We'll make 3 ints, gcost, hcost and fcost, which we went through earlier. Make sure you make the f in an fcost a capital letter to avoid a naming violation. And since we don't need to directly edit fcost, we can just use a get function that adds gcost and hcost together. And finally, the constructor. As arguments, it will take a boolean to set the wall variable, a vector 3 to set the position, and 2 ints to set the grid position. And then we'll just set each of the variables for the nodes to the given arguments. That's the node class complete. The next one we'll do is the grid class. This draws the grid and stores all of the node arrays. To start with, we'll need to declare a few variables. First, a public transform called start position. This is where the program starts pathfinding from. We'll make a public layer mask so that the program can compare against it when looking for obstructions on the map. A vector 2 to store the width and height of the graph in real world units. 2 public floats, one for the size of the nodes and another that controls how far apart the nodes spawn from each other. Now we want to declare the 2-dimensional array of nodes. We're using a 2-dimensional array so it's easier to read, but a 1-dimensional array would be better. Then another list called final path, which will store the completed path that A* finds. A float to store the diameter of the nodes. This will just be double the radius. And finally, 2 ints that will store the position of the nodes in array unit. The first function we need is the start function. Here we'll set the diameter to be twice the radius. Then we'll divide the size of the grid by the size of the nodes on both axes and round it up to the nearest integer using math round to int function. And then we can create the grid. The grid create function will just be a void and won't take any arguments. First, we'll create the node array using the sizes that we calculated in the start function. Then we'll need to find the bottom left of the graph in world coordinates. To do this, we'll use some vector math. It boils down to getting the position of the grid world object, then subtracting the rightmost position of the graph multiplied by half the graph size. And then the same for the other axis as well. We'll then use a double for loop to loop through the array of nodes one by one. Then get the world position of the current node by multiplying the x and the y of the bottom left by the node size and the gap between the nodes. Then we'll determine whether or not the current node is a wall node. We'll declare a boolean and set it to false. We'll then do a collision check against the world position in the node radius and check if it is colliding with anything with a wall mask. If it is, we'll set the boolean to true. We'll then just create a new node in the array at that position using the variables we just calculated as the arguments. Next, we'll actually draw the grid using Unity's gizmos. First, we'll declare the grid box so that we can control the size of the grid. Next, we'll do a quick check to see if the grid has been initialized to avoid any null reference errors. And then loop through each node in the array and check if they're a wall or not. If they are a wall, we'll set them to yellow, and if they're not a wall, we'll set them to white. Then we'll add the part that draws the path. First checking if the final path list is empty, and then if it contains the current node being searched. If it does, we'll set that node to a red colour. Then the last part is to draw out the cubes using the drawCube function. After that, if we go into Unity, create an empty object called Game Manager. And drag the grid script onto it. Drag the start pause block onto the script. Select the wall mask. Set the grid size to what you want. Node radius can be what you want, but if you put it too low, it will cause lots of lag since there will be thousands of nodes on the graph. Now, if we play the program, you should be able to see the graph with your obstacles a different colour. Now we'll make the actual Pathfinding class. First, we'll declare 3 variables. 1 grid member to reference the grid class, and 2 public transforms for the start position and the target position. The first function we'll write is the awake function. This will just grab the reference to the grid class member using getComponent. The next function is the update function. This will just call a function called findPath every frame. We'll pass our start position and end position as arguments. Next we'll write the findPath function, which takes two vector frees as arguments to represent the start position and the target position. First we'll create a node and use a function to get the closest node from the given world position. We'll need to write this in the grid class, so let's quickly go back to our grid script. This function will take a vector free as an argument to hold the position that we'll check. To start, we'll declare two variables that convert the world position to a position in the node array. We'll then clamp those variables between 0 and 1 using the mathClampO1 function, so that if the target leaves the grid area, you won't get an out of range error. We'll then create two new variables, x and y, which multiply the grid size by the variables we just calculated and rounding it to an int, which will give us the correct position in the node array. We'll then just return the node we found at that point. Now we can go back to the pathfinding script and copy that line, and do the same for the target position. Next we'll create one list of nodes called openList. This will store the set of currently discovered nodes that we haven't evaluated yet, and a hash set of nodes called closeList. A hash set is the same as a list, but doesn't hold any values for variables, which is perfect for the closed set, since once a node is in the closed set we don't need to check it anymore. We can then add the starting node to the open list to start the pathfinding process. We can then create a while loop that runs whilst the open list count is greater than 0. Then create a node called current node and set that to the first object in the open list. We'll then use a for loop to iterate through all of the objects in the open list, starting from the second object. We'll use an if statement to check if the f cost of the current open list object is less than the f cost of the current node, and if the h cost is less than the h cost of the current node. If it is, then we can set the current node to the current open list object, since that object is closer to the goal than the current node. After the for loop is finished, we can remove the current node from the open list and add it to the closed list. We can then check if the current node is the target node. If it is, then the program has found a path to the goal, which means we can call the getFinalPath function. We'll write the getFinalPath function below the findPath function. It will take two nodes as its input, the start node and the end node. We'll create a list to store the final path in, and we'll create a node called current node which will store the end node in. Create a while loop that runs while the current node is not equal to the start node. During this loop, we want to add the current node to the final path and set the current node to the node that the current node came from. We can do this by setting the current nodes to the current node's parent. After the while loop, reverse the final path to get the correct order, and then we can set the final path variable in the grid class to the final path variable we just made. Now go back to where we left off in the findPath function and create a for each loop that loops through all neighbouring nodes of the current node. To do this, we'll have to create a function in the grid class again. We'll create this one below the node from world position function we made earlier. It will return a list of nodes and take a single node as an argument. The first thing we need to do is declare a list of nodes called neighbouring nodes. Then declare two ints called xcheck and ycheck. We'll use these to check if the neighbour we're checking is within the graph's range to avoid any out of range errors. To check the right side neighbour of any given node, we can just set xcheck to the grid x of the node and add 1, then set the ycheck to the grid y of the node. Then we'll use an if statement to check if the given node is between 0 and the size of the grid on both axes. If both statements return true, then we can add the node to the neighbour list. Then we just have to repeat this function 3 more times to check the other 3 nodes around the given node. For the left side, we subtract 1 from xcheck instead of adding 1. Then for top and bottom, we do the same as left and right but on the ycheck instead. Then we can just return the neighbour list. Now return to where we left off on the pathfinding script. Write an if statement that checks if the current neighbour node that's being checked is either a wall or if it is already in the closed list. If it is, then we just have to continue to skip that neighbour. Next, we have to calculate the cost of moving to that neighbour. To do this, make an int called moveCost and set it to the gcost of the current node plus the Manhattan distance of the current node and the neighbour node. We can write the getManhattanDistance function at the bottom of the script. It will return an int and take 2 nodes as an argument. All it does is subtracts the grid x and grid y from both of the nodes and returns the sum of them. Next, write an if statement which checks if the move cost is less than the neighbour node's gcost, or if the open list does not already contain the neighbour node. If true, set the neighbour node's gcost to the move cost, the hcost to the Manhattan distance of the neighbour node and the target node, and the parent of the neighbour node to the current node. Check the open list doesn't contain the neighbour node, and if it doesn't, add it to the open list, and then we should be done. Go back to Unity and drag the pathfinding script onto the game manager object. Drag the start position and the target position onto the script in the inspector. Then when you click play, the red path should appear between the start and the target.